Hello everyone. Today we will continue with elementary number theory. First of all, let me introduce prime and composite. A positive integer is called a prime if it has exactly two positive factors. A positive integer is called prime if it has exactly two positive factors. A positive integer is called composite. A positive integer is called a composite if it has more than two. A positive integer is called a composite if it has more than two positive factors. A positive integer is called a prime if it has exactly two positive factors. A positive integer is called a composite if it has more than two positive factors. So let me show you a simple example first. For each of the following numbers, for each of the following integers, determine whether it's a prime or composite. For each of the following numbers, for each of the following integers, determine whether it's a prime or composite. Number 17. Is 17 prime or composite? The only factor for 17 is 1 times 17. The only factor for 17 is 1 times 17. So 17 has only two factors. 17 is a prime. 17 is a prime since it has exactly two positive factors. One and 17. 17 is a prime. It has exactly two positive factors, 1 and 17. How about number 2? Is number 2 a prime? Is number 2 a prime? The only factor for number 2 is 1 and 2. The only positive factor for number 2 is 1 and 2. So number 2 is a prime. Since it has exactly two positive factors. One and 2. Number 2 is a prime. It has exactly two positive factors, 1 and 2. Next, how about number 9? Is number 9 a prime? 9 can be written as 1 times 9 or 3 times 3. So 9 has three factors, 1, 3, and 9. Number 9 has three factors, 1, 3, and 9. Since number 9 has three factors, 3 positive factors. One, 3, and 9. Then we know number 9 is a composite. Number 9 is a composite. Since number 9 has 3 factors, 1, 3, and 9, number 9 is a composite. How about 12? Is 12 a prime? Is 12 a prime? 12 can be written as 1 times 12, 2 times 6, or 3 times 4. So 12 has 1, 2, 3, 4, 5, 6. 12 has 6 factors. 12 has 6 factors, so it's not a prime, it's a composite. Since 12 has 6 positive factors, one, 2, 3, 4, 6, 12. Since 12 has 6 positive factors, 1, 2, 3, 4, 6, 12, then 12 is a composite. If a number has exactly 2 positive factors, it's called a prime number. If a number has more than 2 positive factors, it's a composite. If a number has exactly 2 positive factors, it's a prime. If a number has more than 2 positive factors, it's a composite. Note: is number 1 prime or composite? Is number 1 prime or composite? Number 1 has only one factor. Number 1 has only one positive factor, which is 1. Since number 1 has only one factor, since number 1 has only one positive factor, since number 1 has only one positive factor, it's neither prime nor composite. It's neither a prime nor a composite. Since number 1 has only one positive factor, it's neither a prime nor a composite. So keep this idea in mind. Number 1 is neither a prime nor a composite. Next, let me show you a theorem called unique prime factorization theorem. Unique prime factorization theorem. Unique prime factorization theorem. Sometimes we write it as UPFT. Unique prime factorization theorem. The name is too long. Sometimes we write it as UPFT. Unique prime factorization theorem. This theorem says, for all integers greater than 1, for all integers greater than 1, either itself is a prime. Either it's a prime itself, for all integers greater than 1, either it's a prime itself, or it can be written as a product of prime. For all integers greater than 1, either it's a prime itself, or it can be written as a product of primes in a unique way. Either itself is a prime, or it can be written as a product of primes in a unique way, after an order of factors. Means if we don't care about an order, it can be written as a product of prime in a unique way. If we don't care about a vector, the orders. So, for all integers greater than 1, either it's a prime itself, or it can be written as a product of primes in a unique way, after an order of the factors. That means if we don't care about an order, this number can be written as a product of primes in a unique way. If we don't care about orders. We don't care about order means we consider 3 times 5 is in a sense 5 times 3. If we don't care about order, that means we consider 3 times 5 is in a sense 5 times 3. 2 times 3 times 10 is in a sense 10 times 2 times 3. That means if we don't care about order, 2 times 3 times 10 is in a sense 10 times 2 times 3. That's what it means. Up to order of prime, up to order of factors. This is called unique prime factorization theorem. For every number greater than 1, either itself is a prime, or it can be written as a product of primes in a unique way, assuming we don't care about an order. Now let's do a simple example. Find the prime factorization for each of the following numbers. Find the prime factorizations for each of the following integers. How do we find a prime factorization for 24? We can use factor tree. 24 can be rewritten as 4 times 6. Number 4 can be rewritten as 2 times 2. 6 can be rewritten as 2 times 3. Which is 2 to the power 3 times 3 to the power 1. This is called a prime factorization of 24. This is called prime factorization of 24. How about 100? How about 100? For 100, I can write it as 10 times 10. I can factor 10 as 2 times 5. Factor 10 as 2 times 5. That can be rewritten as 2 squared times 5 squared. We have number 2 twice, number 5 twice. This is called prime factorization of 100. This is called prime factorization of 100. Next, how do we find prime factorization for 1001? How do we find prime factorization for 1001? This number is very big. What can we do? How about this number? This number is also very big. How can we find point factorization for these two numbers? Next, let me show you a theorem. Before I show you how to do this, let me show you a theorem first. Let me show you a theorem. Theorem. Let n be an integer with n greater or equal to 2. If n is a composite, then n has at least one prime factor less than or equal to square root of n. Let n be an integer with n greater or equal to 2. If n is a composite, then n has at least one prime factor less or equal to square root of n. How do we prove it? For this theorem, we can try to prove by contradiction. So, since n is a composite, then by unique prime factorization theorem, since n is a composite, then by the unique prime factorization theorem, n can be written as a product of primes P1 times P2 times Pk. Since n is a composite, then by unique prime factorization theorems, n can be written as a product of primes. That's unique prime factorization theorem. That's what it says here. For any integer greater than 1, either itself is a prime, or it can be written as a product of primes. Since n is a composite, it's not a prime. We can write it as a product of primes, where P1, P2, Pk are primes. Where P1, P2, Pk are primes, and k must be greater or equal to 2. K greater or equal to 2 means n must be the product of at least 2 primes. K greater or equal to 2 means n must be a product of at least 2 primes. If there's only one prime, then n is a prime. Since n is a composite, n must be a product of at least 2 primes. So k must be greater or equal to 2. Now, by contradiction, assume the opposite of the conclusion. Assume the opposite of the conclusion. The conclusion says n has at least one prime factor less than or equal to square root of n. The opposite is all factors of n, all prime factors of n, all prime factors of n must be greater than or equal to square root of n. Must be greater than square root of n. The conclusion says at least one. There is a prime such that this prime is less than or equal to square root of n. Its opposite its opposite, the negation is how to find the negation? For quantifier, if I bring not inside, it becomes for all p must be greater than square root of n. When we bring negation inside, existing quantifier becomes universal quantifier. Less than or equal to, the opposite is greater than. So that's how we find the negation of the conclusion. That's how we find the negation of the conclusion. The conclusion says at least one prime factor is less than or equal to square root of n. There exists one prime factor which is less or equal to square root of n. Negate the statement. If I bring negation inside, existing quantifier becomes universal quantifier. Less than or equal to become greater than. This says all prime factor of n must be greater than square root of n. That's how we negate the conclusion. So assume the opposite of the conclusion. We try to show that's impossible. Here we assume all prime factors of n must be greater than square root of n. Then we can say P1 is greater than square root of n. P2 is greater than square root of n. And Pk is also greater than square root of n. So n equal to P1 times P2 times Pk. It must be greater than square root of n times square root of n times square root of n k times. Because P1 is greater than square root of n, P2 is greater than square root of n, every prime is greater than square root of n. So this number is greater than square root of n times itself, k times. This is square root of n raised to power k. This is square root of n raised to power k. And then since k is greater or equal to 2, this number is greater than or equal to square root of n squared. Since k is greater or equal to 2, this number is greater than or equal to square root of n to the power 2, which is n. Here we have n greater than n. That's impossible. Here we have n greater than n. That's impossible. It's a contradiction. Here we have n greater than n. That's impossible. N must equal to n. Here n is greater than n. So that's contradiction. Once we find a contradiction, that means our assumption was wrong. Since I assume the opposite of the conclusion, if the assumption was wrong here, this conclusion must be true. Since we assume the opposite of the conclusion, and if the assumption is wrong, the conclusion must be true. Therefore, n has at least one prime factor. Since the assumption was wrong, the opposite of the assumption must be true. So n has at least one prime factor. Less than or equal to square root of n. Since the assumption was wrong, the opposite of the assumption must be true. Now let's go back to the previous problem. How do we find the prime factorization for the numbers 1001 and 2047? Those are very large numbers. How do we find the prime factorization? Use this theorem. If a number n is a composite, then n has at least one prime factor less than or equal to square root of n. In the previous problem, for 1001, if we try to find the prime factorization, take square root first. Square root of 1001 is about 31.63. Then we try to list all prime numbers less than 31.63. Now try to list all prime numbers less than 31.63. So prime numbers less than 31 is about, we have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and 31. Those are the prime numbers less than or equal to 1001. Then let's try each numbers. 1001 divided by 2 is not a whole number. If we take 1001 divided by 2, we don't get a whole number. So 2 is not a prime factor. Take 1001 divided by 3, use your calculator. Take 1001 divided by 3, we don't get a whole number. So 3 is not a prime factor. Take 1001 divided by 5, we don't get a whole number. So 5 is not a prime factor. Use your calculator. Take 1001 divided by 7. 1001 divided by 7, we get 143. 1001 divided by 7, we get 143. That means 7 is a prime factor of 1001. 1001 divided by 7, we get a whole number. That means 7 is a prime factor of 1001. So 7 is a prime factor. 1001 can be written as 7 times 143. Now, how about 143? Is 143 a prime? Is 143 a prime? Let's keep going. Take 143 divided by 7. Keep going. Take 143 divided by 7. We don't get a whole number. So 7 is not a prime factor of 143. Take 143 divided by 11. 143 divided by 11, we get 13. That means 11 is a prime factor of 143. And 143 can be factored as 11 times 13. So the prime factorization for 1001 is 7 to the power 1 times 11 to the power 1 times 13 to the power 1. That's the prime factorization for 1001. Now, how about 2047? How about 2047? In order to find prime factorization for 2047, we first of all take square root. Square root of 2047. If I use my calculator, it's about 45.24. Then we know that all prime factor of 2047 must be less than square root of 2047. It must be less than 45.24. So just write down all prime factors. Let's write down all primes less than 45.24. So let's write down all primes. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 30, 37, 41, 43. Those are all primes less than 45.24. Those are all primes less than 45.24. Then we try each number individually. 2047 divided by 2, we don't get whole number. So 2 is not prime factor. 2047 divided by 3, we don't get whole number. So 3 is not prime factor. 2047 divided by 5, we don't get whole number. So 5 is not prime factor. 2047 divided by 7, we don't get whole number. So 7 is not prime factor. 2047 divided by 11, use your calculator. 2047 divided by 11, we don't get whole number. So 11 is not prime factor. Then use 2047 divided by 13. Use your calculator, we don't get whole number. 13 is not prime factor. Take 2047 divided by 17. We don't get whole number. So 17 is not prime factor. Take 2047 divided by 19. We don't get whole number. 2047 divided by 23. Yes, we get whole number now. If we take 2047 divided by 23, we get 89. So that means 2047 can be factored as 23 times 89. 2043 can be factored, 2047 can be factored as 23 times 89. Now, is 89, 23 is a prime. Is 89 a prime? Is 89 a prime? Square root of 89 is about 9 point something. It's a little more than 9, but it's less than 10. Square root of 89 is a little more than 9, but it's less than 10. So, and all prime numbers less than 9 is not a factor. All prime factors less than 9 is not prime factor here. So the 89 must be a prime. All prime factors here, 2, 3, 5, 7. They are not prime factor. All prime factors less than 9 is 2, 3, 5, 7, and they are not prime factors. So 89 is also a prime. Since both 23 and 89 they are both primes, 2047 can be written as 23 to the power 1 times 89 to the power 1. That's the prime factorization for 2047. Next, let me introduce the contrapositive of the previous theorem. Usually for statement P implies Q, its contrapositive is not Q implies not P. For theorem P implies Q, its contrapositive is not Q implies not P. In the previous theorem, if N is composite, this is P. Then N has at least one prime factor less or equal to square root of N. This is Q. That's P, that's Q. So for contraposition, we use not Q implies not P, which says the opposite. If N doesn't have a prime factor less or equal to square root of N, then N is not a composite. If N doesn't have a prime factor less or equal to square root of N, then N is not a composite. So the contrapositive of the previous theorem says, let N be an integer with N greater or equal to 2. If N does not have a prime factor, less than or equal to square root of N, this is not Q. The opposite of the conclusion here. If N doesn't have a prime factor less or equal to square root of N, then not P. If not Q, then not P. P says N is a composite, so not P says N is not a composite. If N is not a composite and N is greater than 2, it must be a prime. Then N is a prime. Since N is greater than 2, if N is not a composite, N must be a prime. This is the contrapositive of the previous theorem. This is the contrapositive of the previous theorem. Since the previous theorem has been proved is true, this is also true. Since the previous theorem is true, this statement is also true. Usually we use this theorem to determine if a number is a prime or not. Usually we use this theorem to determine if a number is a prime. So look at the following examples. For each of the following numbers, determine whether it's a prime. For each of the following numbers, determine whether it's a prime. First number, 359. Determine whether this number is a prime. So, to determine if this number is a prime, we first of all take square root for this number. Square root of 359. Use calculator, it's about 18.94. Use my calculator, it's about 18.94. Then we try to check all prime numbers less than 18.94. Now let's write down all prime numbers less than 18.94. You have 2, 3, 5, 7, 11, 13, 17. Those are all prime numbers. Less than 18.94. Then we check each one individually. If we take 359 divided by 2, there's a remainder. If I take 359 divided by 2, we don't get whole number. So 2 is not factor. 2 is not prime factor of 359. Check 3. Take 359 divided by 3. We don't get whole number. So 3 is not prime factor of 359. Take 359 divided by 5. And we don't get whole number. That means 5 is not prime factor of 359. Take 359 divided by 7. We don't get whole numbers. That means 7 is not prime factor of 359. Next, take 359 divided by 11. Take 359 divided by 11. And we don't get whole number. That means 11 is not prime factor of 359. Then take 359 divided by 13. Take 359 divided by 13. We don't get whole number. That means 313 is not prime factor of 359. Then take 359 divided by 17. Take 359 divided by 17. We don't get whole number. That means 17 is also not prime factor of 359. So since 359 doesn't have a prime factor less or equal to square root of 359, it's a prime. Since 359 does not have a prime factor less than or equal to square root of 359, then it's a prime. Then 359 is a prime. Next, how about 7,117? Is this number a prime? So let's first of all take square root. Square root of 7,117. Use my calculator. I get 84.36. So let's write down all prime factors less than 84.36. Let's write down all prime factors less than 84.36. We have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 51, 59, 61, 67, 71, 73, 79, and 83. Those are prime factors less or equal to 84.36. Those are prime factors less than or equal to 84.36. Then check each prime number individually. If none of them is a factor of 7,117, if none of them is a factor, then this is a prime. But if all of these numbers are not factors of 7117, then this number is a prime. If one of these numbers divides 7117, then this number is a composite. But if none of these numbers divides this number is a prime. Let's check. 7117 divided by 2, we don't get a whole number, so 2 is not prime factor. 7117 divided by 3, we don't get a whole number. 3 is not prime factor. 7117 divided by 5, we don't get a whole number, so 4 is not prime factor. 7117 divided by 7, we don't get a whole number, so 7 is not prime factor. 7117 divided by 11, if I use my calculator, 7117 divided by 11, if I use my calculator, I get 647. If I get whole number, that means 7117 equal to 11 times 647. When I divide, I get whole number. That means 11 is a prime factor. When I take 7117 divided by 11, I get a whole number. That means 11 is a prime factor of 7117. So 7117 equal to 11 times 647. Since 7117 can also be written as 1 times itself, then this number 7117 has at least 4 positive factors. Here we see at least 4 positive factors. Then it must be a composite. Since 7117 has more than 2 positive factors, since this number 7117, it has at least 4 positive factors. Then we can say it has more than 2 positive factors. Then it must be a composite. Since it has more than 2 positive factors, it must be a composite. Since this number has more than 2 positive factors, it must be a composite. Next, let me show you a theorem. There are infinitely many primes. How do we prove it? Direct proof seems impossible, so let's try to prove by contradiction. There are infinitely many primes. Try to prove by contradiction. Prove by contradiction. Assume there are finitely many primes. Assume there are finitely many primes. Call P1, P2, Pk. Assume there are finitely many primes. P1, P2 up to Pk. Assume there are k different primes. Assume there are k primes. Assume there are finitely many primes. P1, P2 up to Pk. Assume there are k primes. And we put this number in order. With P1 is less than P2, P2 is less than P3, and eventually is less than Pk. So assume there are finitely many primes called P1, P2, Pk, and put them in order. P1 is less than P2, P2 is less than P3, and eventually is less than Pk. Pk is the largest prime. Pk is the largest prime. So since Pk is the largest prime, then for any integers greater than Pk, Since pk is the largest prime, then for any integers greater than pk, it must be a composite. Or it cannot be prime. Since pk is the largest prime, then for any integers greater than pk, it cannot be a prime, since pk is the largest. Now, next. Let me define a new number. Let p equal to p1 times p2 times pk. Let p equal to p1 times p2 times pk plus 1. Then p is clearly greater than pk. Let p equal to p1 times p2 times pk. Let p equal to the product of all prime numbers plus 1. Then clearly p is greater than pk. Since p is greater than pk, then p cannot be a prime, since pk is the largest prime. So p cannot be a prime. It must be a composite. Then p must be a composite. Since it's not a prime, it must be composite. Then by the unique prime factorization theorem, since p is not prime, we can write p as a product of primes in a unique way. By unique prime factorization theorem, I can write p as a product of prime. P can be written as a product of primes. By unique prime factorization theorem, since p is not prime, p can be written as a product of primes. Since p is not prime, by unique prime factorization theorem, p can be written as a product of primes, and those are primes. Let pi be one of the prime of p. Let pi be one of the prime factor of p. Since p can be written as a product of primes, let pi is one of these primes. Let pi be one of the prime factor of p, since all primes are here. A prime factor of p must be one of these numbers. So let pi be one of the prime factor of p. Then pi divides p. Since pi is a prime factor of p, pi divides p. Here I is the index between 1 and k. I is the index between 1 and k. I could be 1, 2, 3, 4, 5 up to k. Pi is one of the factors. I is the index between 1 and k. Also, if I multiply p1, p2 up to pk together, if I multiply all prime together, pi is one of the prime. So this number is a multiple of pi. This number is a multiple of pi. So I can say pi divides this number. Since this number is a multiple of pi, I can say pi divides this number. Since pi divides p, and pi divides p1, p2 up to pk, then Then by a theorem we learned last class, if A divides B, A divides C, then A divides any linear combination of B and C. That's a theorem we learned last class. If A divides B, A divides C, then A divides any linear combination of B and C with integer coefficients. Suppose the coefficient are integer, then A divides any linear combination of B and C. That's a theorem we learned last class. Here, since Pi divides P, Pi divides another number here. Pi divides any linear combination of these two numbers. Then I can say Pi divides P plus -1 times P1, P2 up to Pk. Since Pi divides P, Pi divides this number, Pi divides any linear combination of these two numbers. Then, but Pi, P equal to P1 times P2 times Pk. P is P1 times P2 times Pk plus 1. Then P plus -1 times P plus -1 times P1, P2, Pk, they're equal to 1. Since P is P1, P2, Pk, P1 times P2 times Pk plus 1, then P1 plus -1 times this number, it cancels this part. What's left is number 1. So P1 plus -1 times this number is 1. So we have Pi divides 1. So here we have Pi divides 1. That means Pi is a vector of 1. That means Pi is a vector of 1. Since the only vector of number 1 is 1, then Pi equal to 1. Since the only vector of number 1 is 1, here Pi is a vector of 1. Since the only vector of number 1 is 1, the only vector of 1 is number 1 itself, so Pi must be 1. If a number divides 1, this number must be 1. That's a contradiction, because this Pi is a prime. Pi is a prime. A prime must be greater than 2. A prime must be greater or equal to 2. Here we see that Pi is 1. 1 is neither a prime nor composite. That's a contradiction. Since Pi is a prime cannot be 1. It's a contradiction. A prime number cannot be 1. A prime number must be greater than or equal to 2. 1 is neither prime nor composite. A prime number cannot be 1. That's a contradiction. Once we find contradiction, that means our assumption must be wrong. If once we find contradiction, that means our assumption must be wrong. There must be infinitely many primes. If once we find contradiction, that means our assumption must be wrong. So there are infinitely many primes. Therefore, there are infinitely many primes. Next, let me introduce the greatest common divisor and the least common multiple, the GCD and LCM. The greatest common divisor and the least common multiple. Let A and B be integers. The largest integer d with d divides A and d divides B. The largest integer d with d divides A and d divides B is called the greatest common divisor. of A and B. The largest integer d with d divides A and d divides B is called the greatest common divisor of A and B, denoted by the GCD of A and of AB. So, if a number d divides both A and B, it's called a common factor, it's called common divisor. If a number d divides both A and B, then d is called common divisor. And since that's the largest integer, since d is the largest integer, it's called the greatest common divisor. It's called the greatest common divisor of A and B, denoted by GCD of AB. The smallest positive integer m with A divides m and B divides m is called the least common multiple of A and B. The smallest positive integer m with A divides m and B divides m is called the least common multiple of A and B, denoted by the LCM, of A and B. If A divides m and B divides m, m is called a common multiple of A and B. If A divides m, m is a multiple of A. If B divides m, m is a multiple of B. If both A and B divides m, m is called a common multiple of A and B. And since m is the smallest such integer, that's called the least common multiple. M is called the least common multiple of A and B. Notation is LCM of AB. This represents least common multiple, and this represents the greatest common divisor. Next, let me introduce a terminology called relative prime. Relative primes. If the GCD of A and B is 1, for any integer AB, if the GCD of AB is 1, then A and B are called relatively prime. A and B are called relative primes. If the GCD of A and B is 1, then A and B, they are called relative primes. Next, let me show you how to find the greatest common divisor and the least common multiple. Keep this idea in mind. Let A and B be integers. And let P1, P2, Pn be prime factors of A and B. Be prime factors of either A or B. Let P1, P2, Pn be prime factors of either A or B. Then A can be written as P1 times alpha 1 times P2 times alpha 2 times Pn times alpha n. And B can be written as then B can be written as P1 beta 1 times P2 beta 2 times Pn to the power of beta n. The greatest common divisor of AB is P1 to the power of the minimum of alpha 1, beta 1, we pick the smaller power, times P2 times the minimum of alpha 2, beta 2, times Pn times the minimum of alpha n, beta n. The LCM, the least common multiple of AB, is P1 to the power of the maximum of alpha 1, beta 1, times P2 to the power of the maximum of alpha 2, beta 2, times Pn times the maximum, Pn to the power of the maximum of alpha n, beta n. That's how we find the greatest common divisor and the least common multiple. The greatest common divisor, it must be a divisor of both A and B. So its power must be less than both A and B. For every prime, its power must be less than both A and B. So we pick the minimum. The greatest common divisor is a divisor of both A and B. The power of every prime must be less than every power in A and B. The least common multiple of AB, it's a multiple of A and B. So its power must be larger than both power of A and B. Its power for every prime must be larger than the power of A and B for every primes. Since it's a multiple, its power must be larger than the power in A and B. So that's how we find the greatest common divisor and the least common multiple. For the greatest common divisor, we choose the minimum power for every prime. For the least common multiple, we choose the maximum power for every primes. Next, let's do some simple examples. For each of the following pairs of integers, find their GCD and LCM. Suppose I give you two numbers, 300 and 245. How do we find their GCD and LCM? First step, find the prime factorization for both numbers. First step, find the prime factorization for both numbers first. Use factor tree. 300 can be factored as 10 times 30. 10 can be factored as 2 times 5. 30 can be factored as 3 times 10. And 10 can be factored as 2 times 5. The end of branch is 25325. So that's 2 to the power 2, 3 to the power 1, times 5 to the power 2. 245. If we factor, that's 49 times 5. 49 can be factored as 7 times 7. So the prime factorization for 245 is 5 to the power 2, 5 to the power 1 times 7 to the power 2. So the primes in these two numbers prime factors of these two numbers is 2, 3, 5, 7. 2, 3, 5, 7, they are prime factors of these two numbers. So we write 300 as 2 to the power 2 times 3 to the power 1 times 5 to the power 2. There's no 7 here. in 300 there's no 7 here. We write 7 to the power 0. For 245, we write, there's no 2 here, so we write 2 to the power 0. There's no 3 here, we write 3 to the power 0. 5 to the power 1 times 7 to the power 2. Then for the greatest common divisor, we choose the smallest power. For each prime factor, pick the smaller power. For each prime factor, pick the smaller power. I have 2 to the power 0, 3 to the power 0, 5 to the power 1 times 7 to the power 0. For the greatest common divisor, pick the smaller power. Since it must be the divisor, the power must be smaller. Since it's a divisor, it must have smaller power. So 2 to the power 0, 3 to the power 0, 5 to the power 1, and 7 to the power 0. Multiply out, we get 5. That's the greatest common divisor of these two numbers. For the least common multiple, we choose the larger power. For the least common multiple, we choose the larger power. So 2 to the power 2 to the power 2 times 3 to the power 1 times 5 to the power 2 times 7 to the power 2. For the least common multiple, we choose the larger power. Then multiply out. Here I use my calculator, I get 14,700. That's how we find the greatest common divisor and the least common multiple. Next example, how about 40 and 126? Do the same thing. Find the prime factorization for both numbers first. 40 can be factored as 4 times 10. 4 can be factored as 2 times 2. 10 can be factored as 2 times 5. So here at the end of the branch we have 2 to the power 3 times 5 to the power 1. That's the prime factorization for 40. For 126 we can factor as 21 times 6. 21 can be factored as 3 times 7. 6 can be factored as 2 times 3. So here at the end of the branch we have 3723. That's 2 to the power 1 times 3 to the power 2 times 7 to the power 1. That's the prime factorization of 126. Next, we try to find the primes in both numbers. The prime factors in either 40 and 126. The prime factors in either 40 or 126 here is. The prime factors in either 40 or 126 is 2, 3, 5, 7. Put the prime numbers in order. 2, 3, 5, 7. Put the prime numbers in order. That's the primes in either 40 or 126. Then we write 40 as 2 to the power 3 times 3 to the power 0. If there's no 3, we write 3 to the power 0 times 5 to the power 1. If there's no 7 here, write 7 to the power 0. For 126, we write 2 to the power 1, 3 to the power 2. If there's no 5 here, write 5 to the power 0, 7 to the power 1. Then, for the greatest common divisor, we choose the lower power. 2 to the power 1 times 3 to the power 0 times 5 to the power 0 times 7 to the power 0. Multiply together, we get 2. For least common multiple, we choose the higher power. 2 to the power 3, 3 to the power 2, 5 to the power 1 times 7 to the power 1. Multiply together, here I use my calculator, I get 2,520. Next, what if I give you large numbers, for which it's very hard to find their prime factorization? Then what should we do? How can we find their greatest common divisor and least common multiple? What should we do here for large numbers? Let me show you a theorem first. Let me show you two theorems first, then we'll go back to this. Let me show you two theorems first, then we'll go back to this. So we'll go back to this later. Let me show you two theorems first. Let A and B be integers. Then the GCD of AB times the LCM of AB is always the same as A times B. The A and B be integers. The GCD of AB times the LCM of AB is always the same as A times B. How is that? Let's prove it. The A and B be integers. And let P1, P2, Pn be prime factors of either A or B. Then A can be written as P1 alpha 1 times P2 alpha 2 times Pn alpha n, and B can be written as P1 beta 1 P2 beta 2 times Pn beta n. The GCD of AB is P1 to the power of the minimum of alpha 1 beta 1, P2 to the power of the minimum of alpha 2 beta 2 times Pn to the power of the minimum of alpha n beta n. LCM of AB is P1 to the power of the maximum of alpha 1 beta 1 times P2 to the power of the maximum of alpha 2 beta 2 Pn to the power of the maximum of alpha n beta n. Then if we multiply the GCD and LCM, what do we get? If we multiply the GCD and LCM, we add the powers. Since they have the same base, add the powers. We have P1 minimum of alpha 1 beta 1 plus the maximum of alpha 1 beta 1. So for P1, add the power minimum of alpha 1 beta 1 plus maximum of alpha 1 beta 1. Since I don't have enough space here, let me know the last one. I don't have enough space here. I write Pn, multiply everything here, do the same thing. And the last one, for Pn, also add a power. Minimum of alpha 1 times beta 1. Sorry, minimum of alpha n times beta n. Plus the maximum of alpha n beta n. Then GCD of AB times LCM of AB. If we add a power, what do we get? In the class, when we're doing proof by cases, I showed you that the minimum of AB plus the maximum of AB for any numbers a and b, the minimum of ab plus maximum of ab is always a plus b. That's in the class when we are doing proof by cases. I show you this. For any numbers a and b, minimum of ab plus maximum of ab is always a plus b. So same thing here, apply the same rule here. Minimum of alpha 1, beta 1 plus maximum of alpha 1, beta 1. That's alpha 1 plus beta 1. And same thing for P2. I didn't write it here, but for P2, same thing. Minimum of alpha 2, beta 2 plus maximum of alpha 2, beta 2 is alpha 2 plus beta 2. And the last one for Pn. Minimum of alpha n, beta n plus maximum of alpha n, beta n is alpha n plus beta n. That's the same as a multiplied by b. That's the same as a multiplied by b. When I take a times b, I add the powers. P1 to the power of alpha 1 plus beta 1. P2 to the power of alpha 2 plus beta 2. When I multiply ab, I add the powers. So this expression is the same as a times b. This expression is the same as a times b because when I multiply ab, I add the powers. P1 to the power of alpha 1 plus beta 1. P2 to the power of alpha 2 plus beta 2. And Pn to the power of alpha n, beta n. So this is the same as a times b. Let's complete the proof. GCD of AB times LCM of AB is always a times b. Let's complete the proof here. Based on the previous theorem, we have a corollary. For any integers a and b, the LCM of AB can always be written as a times b over the GCD of AB. From the previous theorem, since GCD times LCM is a times b, if we try to solve for LCM, we take a times b divided by GCD of AB. Based on the previous theorem, because GCD of AB times LCM of AB equal to a times b. So in order to find the LCM of AB, I take a times b divided by GCD of AB. That's a corollary of the previous theorem. Sometimes, if we know the GCD of AB, we can use this formula to find the LCM of AB. That's a corollary from the previous theorem. Next, let me show you a different theorem. Let A, B, Q, R be integers. Let A, B, Q, R be integers with A equal to BQ plus R. Let A, B, Q, R be integers with A equal to BQ plus R. That means if I take A divided by B, I can find the quotient Q and remainder R. If I take A divided by B, I can find the quotient Q and remainder R. Let A, B, Q, R be integers with A equal to BQ plus R. By division algorithm, if I take A divided by B, I can find the quotient Q and remainder R. Now, let A, B, Q, R be integers with A equal to BQ plus R. Then, the GCD of AB, the greatest common divisor of AB, is the same as the GCD of BR. If A is BQ plus R, then the GCD of AB is the same as GCD of BR. Let's prove it. For this problem, in order to prove the greatest common divisor of AB and BR is exactly the same, we try to prove they have exactly the same common factors. So in this problem, in order to show the GCD of AB is the same as GCD of BR, we try to show that AB and BR they have exactly the same common factors. Here we try to show that A, B, and BR they have exactly the same common factors. If they have exactly the same common factors, their greatest common factor must be the same. If they have exactly the same common factors, then their greatest common factor must be the same. So we try to show that every common factor of AB is also a factor of BR. Every common factor of AB is also a common factor of BR. And every common factor of BR is also common factor of AB. That's how we show they have exactly the same common factors. Every common factor of AB is a common factor of BR. And every common factor of BR is a common factor of AB. So let's prove it. Let D be a common factor of AB. Let D be a common factor of A and B. We try to show that D is also a common factor of BR. Let D be a common factor of AB. Then D divides A and D divides B. If D is a common factor of AB, then D divides A and D divides B. We try to show that D is also a common factor of BR. Let me show D divides B and D divides R. Here we already know D divides B. What's left is to show D divides R. Here we already know that D divides B. What's left is to show D divides R. Now here we have D divides A, D divides B. Then since D divides A, then D times the number K equal to A, and D times the number L equal to B. If D divides A, then D times the number K equal to A. If D divides B, then D times the number L equal to B, where K and L are integers. Since A equal to BQ plus R. Since A equal to BQ plus R, I can solve this equation for R. Then R equal to A minus BQ. Then R equal to A minus BQ. So R equal to A minus BQ. A is dk. B is dl. A is bk. D is bl. Then I can factor D out. Then I can factor D out. Then I can factor D out. If I factor D out, I have K plus LQ. That's an integer. Because K and L, they're both integers. And A, B, Q are also integers. So this is an integer. Since R equal to D times K plus LQ, and where K plus LQ is an integer, then D divides R. Since R equal to D times the integer, then D divides R. Here R equal to D times the integer, then D divides R. Since D divides B and D divides R, then D is a common factor of B and R. So here we show that every common factor of AB is a common factor of BR. Here we show that every common factor of AB is a common factor of BR. Next, we try to show that every common factor of BR is a common factor of AB. Next, let E be a common factor of BR. Next, let E be a common factor of BR. Then, since E is a common factor, E divides B and E divides R. We try to show that E divides A and E divides B. We try to show that E divides A and E divides B. We already know that E divides B. What's left is to show E divides A. Since A equal to since E divides B, I can write EK equal to B. Since E divides R, I can write EL equal to R. If E divides B, then E times the integer equal to B. If E divides R, then E times the integer equal to R. Then, where K and L are integers, then A equal to BQ plus R. Since A equal to BQ plus R, I can replace B with EK. I can replace B with EK. I get EKQ. Replace R with EL. Then I can factor E out. If I pull out E, I get KQ plus L. Since K and L are integers, Q is also integer. This is an integer. Since A equal to E times KQ plus L, where KQ plus L is an integer, then since A equal to E times some integer, then E divides A. Since E divides A and E divides B, then E is a common factor of AB. Then E is a common factor of AB. Since E divides A, E divides B, E is a common factor of AB. Here we can see that every common factor of BR is a common factor of AB. And every common factor of AB is a common factor of BR. That means they have exactly the same common factors. Since every common factor of AB is a common factor of BR, and every common factor of BR is a common factor of AB, then AB and BR, they must have exactly the same common factors. Therefore, AB and BR, they must have exactly the same common factors. If they have exactly the same common factors, their greatest common factor must be the same. Hence, their greatest common factor must be the same. So, GCD of AB is the same as GCD of BR. That means this theorem says if I divide A by B, the GCD of AB, I can remove A and replace it with the remainder. The GCD stays the same. For GCD of AB, if I take A divided by B, if I take A divided by B, let R be the remainder. Then, for GCD of AB, I can remove A and replace it with the remainder. The GCD stays the same. For GCD of AB, if I remove A and replace it with the remainder, the GCD stays the same. Now let's go back to these two problems here. How do we find their GCD and LCM? Look at number 3 first. We have 6,881 and 203. We try to find their GCD and LCM. Let's find their GCD first. If we can factor these two numbers, for GCD, how do we find GCD of 6,881 and 2003? Do division. Take larger number, divide by the smaller number. 6,881 divided by 203. Remainder is 182. If I take 6,881 divided by 203, remainder is 182. So, by the previous theorem, if I replace the larger number with a remainder, if I replace the dividend with a remainder, the GCD stays the same. By the previous theorem, A equal to BQ plus R. A is called dividend, B is the divisor, R is the remainder. If I replace the dividend with a remainder, the GCD stays the same. If I replace the dividend with a remainder, the GCD stays the same. So this number is a dividend. If I replace the dividend with a remainder, the GCD stays the same. Next, same thing. Use do division. Take larger, divide by smaller. Take 203, divide by 182. I get 21. So 203 is a dividend. 21 is a remainder. If I replace the dividend with a remainder, the GCD stays the same. If I replace the dividend with the remainder, the GCD stays the same. And keep going, take the dividend, take the larger number, divide by the smaller number. Take 182, divide by 21. The remainder is 14. If I replace the dividend with a remainder, the GCD stays the same, according to the previous theorem. If I replace the dividend with the remainder, the GCD stays the same. Then, keep going. Take larger number, divide by smaller number. Take 21, divide by 14. Remainder is 7. Then 21 is a dividend, 7 is a remainder. If I replace the dividend with a remainder, the GCD stays the same. Then keep going. Take the larger number, divide by the smaller number. Remainder is 0. I can replace the larger number with a remainder. Replace the dividend with a remainder. I get 0, 7. The greatest common divisor of 0 and 7 is 7. The greatest common divisor of 0 and 7 is 7 because every number is a divisor of 0. And the larger divisor for number 7, the divisor is either 1 or 7. And for number 0, both numbers are divisor of 0. Both number 1 and 7 are divisor of 0. And so 7 is larger. That's called the greatest common divisor of 0 and 7. Because every number is a divisor of 0. And for number 7, the only divisor is 1 and 7. 7 is the larger. 7 is a larger divisor. It's the largest divisor for number 7. So 7 is the largest, is the greatest common divisor for both 0 and 7. So greatest common divisor of 0 and 7 is 7. That's how we find the greatest common divisor. This technique here has a name. It's called the Euclidean algorithm. Euclidean algorithm. This technique here has a name. It's called the Euclidean algorithm. This technique of finding a GCD has a name. It's called the Euclidean algorithm. Next, once we know the GCD, we can find an LCM. LCM of AB is the product of AB divided by the GCD of AB. Once we know the GCD, we can find an LCM using the formula A times B over GCD of AB. So for LCM of AB of these two numbers, take this number 6,881 times 203 divided by the greatest common divisor. Here I use my calculator. I get 199,549. I get 199,449. That's the least common multiple of these two numbers. That's a GCD. That's an LCM. That's the example. How do we find a GCD and LCM for this number? 126,492 and 1,591. How do we find a GCD and LCM? For the GCD, we can use Euclidean algorithm. 126,492, 1,591. Then do division, do long division. Take the larger number, divide by the smaller number. 126,492 divided by 1,591. Here I use my calculator. 1,591 goes into this large number 79 times. 79 times 1,591 591 is 1, 2, 5, 6, 8, 9 in my calculator. Then subtract. Remainder is 803. By Euclidean algorithm, we replace the larger number, replace the dividend with a remainder. By Euclidean algorithm, replace the dividend with a remainder. I get 803, 1591. Then keep going. Use the larger number, divide by the smaller number. 1591 divided by 803. I get 788. So replace the dividend with a remainder. Replace the dividend with a remainder. Then keep going. Take larger number, divide by the smaller number. I get remainder is 15. So replace the dividend with a remainder. Replace the dividend with a remainder. Then keep going. Take the larger number, divide by the smaller number. 15 goes into 78 5 times. 5 times 15 is 75. Subtract, we get 38. 15 goes into 38 2 times. 2 times 15 is 15. It's 30. Remainder is 8. Then replace the larger number, the dividend with a remainder. Then keep going. Take larger number, divide by smaller number, and take remainder. 15 divided by 8. 8 goes to 15 one time. 1 times 8 is 8. Remainder is 7. Then replace the larger number with a remainder. Then keep going. Take larger number, divide by the remainder. Take larger number, divide by smaller number. 8 divided by 7. Remainder is 1. Replace the dividend. Replace the dividend with a remainder. We have 7 and 1. Then keep going. Take 7 divided by 1. 1 goes into 7 7 times. 7 times 1 is 7. Remainder is 0. Replace the dividend with a remainder. GCD of 0 and 1 is 1. Once we know the GCD, we can find the LCM. LCM is the formula for LCM is we multiply these two numbers, then divide by the GCD. The GCD here is 1. And when I use my calculator, I get a huge number. 201,248,772. That's the LCM of these two numbers. So for large numbers, if we can't find a prime factorization, we must use Euclidean algorithm. Find the GCD first, then use this formula, find the LCM. If we can't find a prime factorization, we must use Euclidean algorithm. Find the GCD first, then use this formula to find the LCM. And this technique here is called Euclidean algorithm. Keep it in mind.